Welcome to lecture 5.5, Impulse Functions. So let me ask you a question, just open-ended. What is the derivative of the Heavyside function? So remember what the Heavyside function is? It's this function, which is 0, and then it jumps up to here. And this up here is 1. So this, of course, is not differentiable, so this question is a little bit ambiguous because the derivative does not exist everywhere. Well, the derivative exists everywhere outside of 0. I mean, every negative number and every positive number is 0, but then it doesn't exist at 0. So again, it's not defined. The derivative is not defined everywhere, but what should it be? If we could define it, if we could cheat a little bit, what should it be? So let me work up to the answer to that question, or I guess one answer. Some people might be stubborn and say, well, it doesn't exist no matter what, and I can understand that. So here is, so what I'm going to do, let's do this. I'm going to draw 4 axes. Actually, let me make this one a little bit, make them a little skinnier so I can fit them all in. I'm going to draw 4 axes. I'm going to put 4 different functions on here. So the first one, this is going to be a function. It's going to be 0 everywhere here. Then it's going to go up like this. Actually, let me even make it more so than that. Let me do this. And let me call this number here, let me call this epsilon 1, and I'll put that back in. And let's suppose that the slope here, so the slope of this function equals 1 over epsilon 1. In other words, this thing up here is 1. So I'm going to draw several of these functions. Let me take a smaller value of epsilon, call it epsilon 2, and then let me take epsilon 3, which is here. And I'm going to draw similar functions. So this is sort of like a Heavyside function, but it's continuous, and it doesn't have this big jump. Okay, so the slope of this obviously is 1 over epsilon 2. The slope down here, let's fix that a little bit. The slope is 1 over epsilon 3. So if you do this in the limit, whatever the heck that means, in the limit, let me make these dots a little bigger, dot, 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 what do you get? So you get the Heavyside function. So in the limit, well, I want to say when epsilon is 0, then the slope of this is 1 over 0, which is infinity. But I can't quite say that. So let me name these functions. I'm going to call this one h sub 0 superscript epsilon 1 of t. So my notation is 0 is where this thing occurs, and epsilon 1 is the width of this. So that's going to make this thing h naught epsilon 2 of t. This is h naught epsilon 3 of t. And this one here is h, let's just call it h of t, the Heavyside function. So I can think of the Heavyside function as being a limit in some sense of these functions. Now I know these things aren't differentiable, but let's suppose we were to take a little bit of sandpaper and sand off this corner and sand off this corner so it were a smooth curve, so it had a derivative. We could do that. And then what would the derivative, actually I don't want to ask what the derivative, what's the derivative? Let me ask that. So the derivative is slope of the tangent line, and if you don't like my sandpaper thing, you can just accept it and say, okay, the derivative is not going to be defined in these 2 points, but it's defined everywhere else. And let me show you what it is. So it's going to have height 1 over epsilon 1. So it's going to be this function. It's going to be an interval function. And let me just put these vertical bars here. So, and let me call this thing delta 0 of epsilon 1 of t. So I'm going to name this function. One thing to note is that the area under the area under the curve is 1. Right? And that makes sense because this function eventually goes up to 1. It has width. This has width epsilon 1 and height 1 over epsilon 1. Okay, so let's do the same thing over here. So here is epsilon 2, and here is maybe this here, I don't know, I'll write this up here, 1 over epsilon 2, and the derivative of this function is this interval function here. Again, the slope is a constant 1 over epsilon 2 in this region, or this interval, and it's 0 elsewhere. So I'm going to call this function delta 0 of epsilon 2 of t, and you see my naming convention. Let's do one more. So this is epsilon 3, and then this has to be way up here, 1 over epsilon 3. Now this function is this thing. And again, both these things have area equal to 1, both under this area, or under this box, under that box. And this thing is delta 0 of epsilon 3 of t. Okay, so same question. In the limit, now it's not always true that we can do this and just take limits because this limit may not exist, but I'm waving my hands a little bit and I'm saying I'm just trying to give you the intuition rather than a rigorous definition of it. So what function should go here? What function do we want to be the derivative of the Heavyside function? Well, it should have, so if I want to think of this as h sub 0 and then epsilon is 0 of t, then this thing here, well, it should be a function that it's 0 for all positive numbers and all negative numbers, and it should somehow, not even sure this is possible, but it should somehow be, it should be infinity up here. Now I'm going to put this in quotes. When I write something in quotes, that usually means I'm lying, so it's technically not defined to be infinity, but that's what we want it to be. And somehow this magic box is going to have width 0 and height infinity, so obviously the area is going to be 1. And obviously it's a little bit sarcastic there. But that's what we would expect. I mean, if you actually do draw the vertical line up here, then this line does have slope infinity, so the derivative should be 0 everywhere else and infinity here, right? Well, so we can actually define a function like this. It's technically not a function, but we can define it and it actually magically works out. Now there is a lot of deep, rigorous mathematics behind the scenes that if you take probably a second semester course in undergraduate real analysis, you'll learn about. But for now, that's way beyond the scope of this course. So we can define this function. It's called the Dirac delta function, frequently just called the delta function, centered at p. Now in the previous slide, we let p be 0, but we can actually do this for any p on the x-axis. So we denote it as delta sub p of t, and it's technically not the limit, but I'm going to say in quotes because I'm appealing to our intuition. It's the limit of this sequence of functions that I showed you in the previous slide as the epsilon goes to 0. And so it's defined, we say it's 0 for all points not equal to p, and it's infinity at that special point t equals p. Okay, so if you're sitting there wondering whether I really am being straight with you or whether I'm cheating with this stuff, like defining a function where it can be infinity sometimes and its area under this curve that has height infinity and width 0 is 1 magically, if you think I might be cheating, well, I completely understand. I felt the same way when I first learned about this in college. I didn't believe it for a long time, and it actually certainly hurt my performance in a particular engineering class. It just didn't seem like it was mathematically rigorous and it had a foundation to stand on, and it seemed like some sort of pseudoscience. But I assure you that it is sound and it does work, even though it may sound a little fishy. So bear with me. Okay, so some properties on this. So this is just a fancy way of saying that the area under the curve, So if we go up to p and we draw the delta function, it's going to be 0 everywhere else and then infinity up here. So it's infinity up here. That the area under this curve is 1. Okay, so a consequence of that, I claim, is that if you integrate, from negative infinity to infinity, take the delta function and multiply it by any old function that you wish. That's defined at p. I claim that this function just picks off, let me erase it just picks off f at p. And I'm going to see if I can try to give justification for why that should be the case. So if this is p, let's say this is 1, then let me try to draw that delta function again. Let's take another function. Let's say this is f of t, and so f of p is up here. This is f of p. So multiplying this function, multiplying the delta function times f of t, and then integrating, this thing should absolutely be the same as, tell me if you believe this, it should absolutely be the same as integrating over the real line the delta function at t times the constant function f of p dt. Okay? So why is that true? Let's take this constant function. Let's draw it here. And so what are you doing? You think of the Riemann sums. To the delta function, it is indistinguishable when you do this integral whether or not you are multiplying the delta function by this constant function or by this function here, because the delta function kills this function f of t at every other point outside of here, so you might as well just be multiplying the delta function times the constant function, in which case you can pull the constant function out of the integral and write this as f of p times, so f of p times this thing right here. Okay, so another consequence of that is that the Laplace transform is really, really simple. So most Laplace transforms are not easy. You got to do integration by parts or something like that. So let me actually verify why this is true. So the Laplace transform of the delta function, that is just the definition. It's 0 to infinity of the delta function f0 of t times e to the minus st dt. So this thing is just by this property right here. I think this is important enough that I actually want to box it. So by this property, this integral is just equal to e to the minus st evaluated at t equals 0, and that's obviously 1. Isn't that neat? So a consequence of this, I claim, is that the Laplace transform of the delta function at p of t, so what's that going to be? Well, I'll show you two ways to do it. So first of all, I claim that this is e to the minus s times p. Maybe I should write p times s because s is my actual variable here. Yeah, p times s. So let me box that as well. One way to see that is well, if you just take the integral, you can do it by from scratch. T. Let me make that a p, and let me make that more of a t times e to the minus st dt. Well, that is just this function evaluated at p. Again, that's just using this property right here. So that is clearly e to the minus s times p, or ps, let's say. Okay, so that checks out. And another way why it's true is because, remember this always useful formula, the Laplace transform of f of f of, not c, sorry, f of t minus c times h of t minus c equals e to the minus s minus c times s, sorry again, c times s times f of s. Well, let's apply this function. Let's apply this to the delta function. So the Laplace transform. So this delta function, this is just a shifted value of the regular delta function. So that's delta 0 of t minus p h of t minus p. And that is e to the minus p times s times f of s, which is 1. And yes, that checks out as well. Okay, so I just realized this is the last slide about solving a differential equation where the forcing term is a delta function. I didn't actually tell you what the delta function represents, so let's do that now. So the delta function represents a unit impulse force. And so what is that? That just means a finite force over an infinitesimal time interval. So over an infinitesimal, wait, I didn't spell that right, did I? Infinite, I'm not sure, I don't think that's right either. Infinitesimal, okay, that's close enough. Time interval. So one example, I like mechanical examples, is suppose you take a hammer and you bang it on the table in front of you and you measure the amount of force per unit time, or I guess at any point in time. So what's going to happen is that you're going to get a blip like this. So for a very small amount of time, you're exerting a large amount of force. And if you remember from physics, and I actually did and I had to look it up, the impulse is the integral, thank you Wikipedia, impulse is the integral of force. So here the impulse is there's a finite amount of impulse exerted on the table because it's just the area under this curve. So the delta function is sort of the ideal of this, whereas you can model it as, instead of this being really, really small and this being really, really tall, you can model it as if you had 1 unit of impulse, then just pretend that had an infinite force over infinitesimal amount of time, and so the area under the curve is the impulse, which is finite. Okay, so I'm sure I know this stuff comes up in electrical engineering. I don't know enough about circuits and things like that, RLC circuits, to give you an example as to what a impulse force is going to be in that situation. I'm sure some of you listening to this are electrical engineers yourselves, and you probably already know. Okay, so let's go back to solving this problem. This is a damped harmonic motion. So think of like a mass spring system with a damper. And at time equals 0, it's sitting at rest in equilibrium. And then at time equals 0, we exert a unit impulse force at it. So we maybe hit it with a hammer. So let's solve this. So the first step before is to apply the Laplace transform. So let's apply the Laplace transform to the left-hand side. So Laplace transform of y double prime plus 2y prime plus 2y. And then on the right-hand side, the Laplace transform of the delta function. Okay, so this thing, normally we need to do each of these separately, but because both of these initial conditions are 0, this thing just reduces down to s squared plus, I'll write it out. So this is going to be s squared y plus sy plus 2y. And again, we don't have those other terms that we have to subtract off because these are both 0. And then the right-hand side, we just get 1. Oh, I forgot parentheses. There we go. We get 1. So let's factor out. So we have s squared plus, oh, sorry, it's 2s, isn't it? Yeah, 2s plus 2 times y equals 1. And so now we have solved for y. Y equals 1 over s squared plus 2s plus 2. Great, and how do we do this? Well, this is actually in that form where we have to complete the square. So let's do that. We have s squared plus 1, I'm sorry, not s squared plus 1, s plus 1 quantity squared plus 1. So this is the Laplace transform of sine. So that means that y of t equals e, sine shifted by 1, e to the, try that again, e to the negative t sine of t. Okay, so let me say a comment or two about this. So one thing you may wonder is this function, if you were to graph it, it actually, so what does it look like? It's, where do I want to do this? It actually does not satisfy the initial condition. So if you were to graph this, it's going to look like, it's a sine wave that is damped. And this thing here is going to get bigger and bigger. However, actually let's write that down. So how do I want to say this? I'll just say it for now. This does not match the initial conditions. Y of 0 equals 0. Well, that works. But y prime of 0 is not 0. Notice that? So what's the problem here? We found this function, but it solves the differential equation, but it doesn't exactly match this. So there is a resolution because technically, when I say we found this function, what we were doing throughout is, I really should say that this function, y of t, is e to the minus t sine of t times the Heavyside function, h of t. Because again, when we were completing the Laplace transform, we did it of the delta function. We really should have done it of the delta function times the Heavyside function. The Heavyside function is always there. So this thing here, we really don't want to. So we really don't want to count this stuff down here. What we want to do instead is this is y of t times h of t. So that's going to make it 0 here. So now it satisfies this initial condition, and it doesn't quite satisfy this, but it's pretty good in that, well, the derivative doesn't exist here, except the left-hand derivative does exist. So let me write this function. So this function is 0 if t is less than or equal to 0, and it's e to the minus t sine of t if t is greater than 0. So again, it's not differentiable at t equals 0, but technically the limit, technically the limit as t goes to 0 from the left of the derivative of h of t, y of t, that thing does equal 0, and that's good enough to match this condition